Okay, so I will introduce you to integrals today very quickly, emphasizing the important things about the integral, about its definition, about its properties. And I'll start with the discussion we began last time about area. So I'll start with the area problem. So the shapes on the plane that we know the area of are going to be, of course, those simple shapes like rectangles, when we know the area is the product A times B. We also know the area of a triangle, and then we compute it using the base and the height. So it is a half of base times height. And based on the computation of the area of a triangle, you can compute the area of any polygon by cutting polygon into pieces. And immediately there, as we cut and compute, we make an assumption that the area is additive. So we use this property of additivity. If we have areas A1, A2, A3 making up the whole area A together, then the area is, total area is the sum of those areas. And then we use this to argue that no matter how you subdivide into triangles, the result is going to be the same. But that's a different story. I don't want to go into that. So we use this key property of additivity to find areas of complicated regions, but those are not very complicated, and the areas of general regions, even of a circle, remain unknown. We cannot subdivide the circle into polygons. So what we do for a circle or for general region is we specify a procedure of how to compute the area. And one of the ways to specify the procedure is calculus way. So we assume that there is a function, and that function is defined on some interval. And we try to find the area under the graph of that function. So we have x and y axis, we have the interval from A to B. The function is defined on that interval. We look at the graph. And the geometric problem is to find the area below the graph and above the x-axis. And what we do is we specify exactly the procedure. The procedure is we subdivide this area into pieces. So what we do is we say we will subdivide into n pieces, where n is a large number. And those pieces are going to be vertical pieces like this. So we have those pieces denote the areas of those pieces by A1, A2, and the last one is going to be nth piece. And then we use additivity. We say that the total area is exactly equal, there is no approximation yet, exactly equal to the sum of all those areas, A1 plus A2 plus dot 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 plus n minus 1 plus an. And this is exactly the place where you want to use something better than notation ... Right? So this is exactly the place where we introduce sigma notation, and it is just a notation. There is no magic about it. It's just a replacement of those ... It is the exact specification of how you make a sum, if the sum is long. If you have a sum of 3 terms or 4 terms, well, write them down as 3 or 4. But as we have sum of many terms, sigma notation is just about writing exactly what this sum is. So when we add up similar things and only one parameter changes in those things, right? Like this index, then we turn that parameter into a variable, let's say I, and then we say I changes from this number 1 to that number n, and what we add up is those areas ai. So this is again just a notation for this sum with ...